All right, hi folks, this is Larry Mussolino. I'm recording a video for Module 11 in Math 181. This has to do with something called Markov systems. And what this is allowing us to do is use probabilities to evaluate changing from one condition to another condition, or sometimes we think of it as changing from one state to another state. Here's some examples. Let's say you're a business major, but you've been thinking about changing to computer science. Let's say right now you're a customer of Verizon for cell phone service, but you're thinking about changing to T-Mobile. Maybe you're driving a gas-powered vehicle, but you've been thinking about purchasing a Tesla, an electric vehicle. So in each of these examples, we want to change from one state to another or from one condition to another. And what we'd like to do is use probabilities to assess this. Maybe you're thinking about buying a Tesla, but you're not really convinced yet. So maybe there's only a 20% chance that you are going to change to an electric vehicle. But maybe you've been with Verizon and their prices are going up. T-Mobile is cheaper. So there's a 90% chance you're going to change to T-Mobile. So we'd like to understand how to transition from one state to another using probability considerations. And that's where this transition diagram comes in. What this allows you to do is get a visual picture of the probabilities for moving from one state to another. So here's how this transition diagram works. This is these blue circles are the states. So let's say state 1 is Verizon cell phone service, and state 2 is T-Mobile. All right, and what you do is you write down the probability of changing from one state to another. So if I'm a Verizon customer now, what's the probability that I'm going to change over to be a T-Mobile customer? Well, according to this, that probability is 0.2. Well, if there's a 0.2 chance that I'm going to change to T-Mobile, that means there's a 0.8 probability that I'm going to stay with Verizon. So this arrow that's pointing back to state 1 is the probability of you staying in state 1, meaning you're going to stay as a Verizon customer. Notice how these two probabilities always have to add to 1, because you're either going to switch to T-Mobile or you're going to stay with Verizon. Those are your only options, let's say, at this point. So these probabilities always have to add to 1. Well, what if I do change to T-Mobile? There's always a chance that I might want to switch back. Well, there's a 0.1 probability that I would go back to Verizon, but then there's a 0.9 probability that I'm just going to stay in state 2. That means staying with T-Mobile. Again, notice how these add up to 1. So this is the way to think about setting up a transition diagram. Now, there's some labeling that goes on here. So let's talk about how to label these probabilities. So what you do is you label these by writing down the state you're in and the state you'll transition to. So if I write P1 subscript 1, 2, this means this is the probability of starting in state 1 and ending in state 2. Well, really, that's this number right here, right? Because this is the probability of going from state 1 to state 2. So this probability 0.2. What about the probability of 1, 1, 1, 1? Well, this is the probability of starting in state 1 and staying in state 1. Well, that's this number right here, 0.8. So what we do is we take these probabilities and put them in a matrix, because we want to do some calculations on these probabilities, and it's going to be easiest to do this in a matrix form. So here's the way you set up the matrix. Let me scroll down a little bit. Here's the way we do the matrix. Let me try to keep this diagram with us here. Hang on one second. I'm just going to take a snapshot of this diagram and bring it down here with us. Okay. All right, so let me put this side by side here. All right, so here's the diagram we have. So the way we want to set up this matrix is we want to put it here as P11, then P12, P21, P22. Okay, and this first row you could see are the arrows that are coming out of state 1. So let's populate this in our diagram. If we're going to write this as P11 here and P12 here, then P11 is that probability where you start in state 1 and stay in state 1. Well, that's 0.8. So that means we're going to put 0.8 in this upper left corner. P12 is the probability that I start in state 1 and transition to state 2. So that means that's going to be this probability 0.2. So I'm going to put that number in the upper right corner of the matrix. Then if I go to the bottom row, it's P21, P22. All right, P21, that's the probability that you start in state 2 and transition to state 1. So that's going to be 0.1. So I'm going to put 0.1 in this bottom left corner. Finally, P sub 22, that's the probability you start in state 2 and stay in state 2. Well, that is this 0.9 number. So that's why this is 0.9. Okay? And you might notice when you add up these probabilities, each row, the probabilities should add to 1. Right? So when you add across the rows, the numbers should add up to 1. All right, so what do you do with this matrix then? Once you've created this matrix, how does it work? Well, what we want to do is give a probability of transitioning from one state to another. So again, let's say we have customers with Verizon. What's the probability that they transition to become T-Mobile customers? That's very important, right? Verizon wants to know that. T-Mobile wants to know that. It would tell a company if they're going to lose market share or gain market share. All right, so let's come up with a diagram. All right, so let's say we are interested in probabilities going from a gas car to an electric car. Okay, so let's say a company assesses the current state. So we need to know what is the current distribution. So for this company, they find out right now 85% prefer gas-powered cars and 15% prefer electric. But they know this is going to change over time because more and more people are considering electric cars. Electric cars are getting better and better, in terms of their range on a full charge. So they know, this company knows over time, people are probably going to start switching to electric. They want to get a sense of what that transition looks like because they need to plan for that, eventual outcome. If this car company decides to stick with gas-powered engines, well, they're probably going to go out of business because, over time, electric vehicles are going to get more popular. The government, some governments are mandating, change over to electric vehicles. So this company wants to get a sense of what this transition is going to look like. All right, so this is, we call this the initial distribution. And we're going to call it a vector because we're going to make this into a row vector. So this is the initial distribution row vector. It's really saying this is the initial state of affairs. All right, now we need a transition matrix. So let's draw a little diagram here. So let's call this state 1. This is the gas-powered car. And state 2, people converting over to electric. All right. And so let's say this company is doing some market studies, and they say there's a 40% chance that a customer will switch to an electric car. So I'm going to write that here and put 0.4 as that probability. Well, if there's a 40% chance that a customer changes from gas to electric, that must mean the remaining probability of 0.6 is people sticking with the gas. So 60% of people are going to stay with gas-powered cars. How about once you're an electric owner? Well, it says there's an 80% chance that they're going to stay with electric and a 20% chance that they might switch back to gas. All right, so this is our diagram. Well, once we have this diagram set up, it's easy to set up the matrix. Remember, we write it as P11, P12, P21, P22. All right, well, P11 is the probability that someone has a gas-powered car and they stay with a gas-powered car. Well, that's 0.6. P sub 12, let me write this a little better here. P sub 12 is the probability that a person has a gas car, but they're going to change to an electric. Well, according to our diagram, that's 0.4. So I'm going to put 0.4 here. All right, so I filled in the transition matrix according to the diagram. Now I want to know this question: how will market share change over time? So what's going to happen to this initial distribution vector? What's going to happen to this initial distribution percentage over time? What's it going to transition to? Okay, and what we're working with here is a 1 year window. So this is looking at out 1 year. All right, so the question is, what's going to happen next year? How is 8515 going to transition to a new distribution? Well, the way you answer that is you take the initial distribution vector and multiply it by the transition matrix. That gives me the distribution after one step. In our example, this will be the new distribution after 1 year, because we're working with 1 year as our time period in this example. All right, so let's do it. Here is the initial distribution vector. Remember, it was 85% for gas cars and 15% for electric cars right now. So this is the state of affairs right now. So I'm going to write this as this row vector. Here is the transition matrix we just came up with. And now we're just going to multiply these two matrices together. Okay, so let me remind you how to multiply matrices together. The way you multiply this matrix is you take the row and multiply it by the first column. So I'm going to take 0.85 times 0.6 plus 0.15 times 0.8. Notice this is taking this row times the first column. And if I work that out on my calculator, I get 0.63. So that's the number to put here. Then I also want to take this same row and multiply it by the second column. So that's going to be 0.85 times 0.4 plus 0.15 times 0.2. If I work that out on my calculator, I'm getting 0.37. That's the number to put in this new distribution. All right, so now we've got this answer. What is our conclusion? Well, the first number, the way we're setting this up is the first number is the gas-powered percentage, and the second number is the electric. So this started out at 0.85, 0.15. Now, after 1 year, our prediction is this is going to transition to be 0.63 to 0.37. So the percentage of people owning electric vehicles is going to jump from 0.15 to 0.37. That's a big jump. That's doubling, more than doubling. The percentage of people that prefer electric will drop significantly from 0.85 down to 0.63. That's a big drop. So this company better plan for a fast transition to electric vehicles. What would happen after the second year? So what about after 2 years? Well, I can repeat the process. I can take this new distribution vector, 0.63 and 0.37. And I can multiply it again times the transition matrix, because I'm going to assume this transition matrix applies year over year. So I could work this out on my calculator and get the new distribution after 2 years. And I could do it again for 3 years, do it again for 4 years. This would give me a good picture of what's going to happen out over the next 5 years, let's say. Okay, so this is the idea of working with this Markov system, it's called. It allows you to take transition matrix, apply it to some initial state of affairs. We call that the initial distribution vector. The answer you get is the new distribution after the transition has taken place. All right, so, and again, you could do this multiple times, right? If I was to take the initial distribution vector and multiply it by the transition matrix 2 times, this would give me the distribution after 2 steps. That would be like after 2 years, for example. Okay. Now, if you keep doing this over and over, there's something called a steady state distribution vector. And that's worked out in the textbook, and it shows you what happens if you were to assume, many applications of this transition matrix, kind of saying to you what happens in the long run. All right, folks, here is a good video to check out from Khan Academy. And why don't we go into WebAssign and do a few examples. So let's do that. Hold on one second. I'm going to go into WebAssign. Bear with me. All right, folks, so I'm here in WebAssign Module 11 homework. Let's do a few representative examples. Folks, a quick reminder, when you see a Watch It button, please check out that video that WebAssign provides. Those videos are very helpful. All right, well, there's a few problems where you're asked to take the diagram, the transition diagram, and convert it into the matrix. So really what you need to remember on this is the setup of the matrix. So remember, the setup is P11, P12, and then P21, P22. So this is the way we want to set it up. What this is the probability that you're in state 1 and you stay in state 1. Well, the probability that I'm in state 1 and I stay in state 1 is 4 over 7. So this is 4 over 7. P12 is the probability that I start in state 1 and go to state 2. Well, I could see that is this 3 over 7. And let me come down here. P2 sub 1, that's the probability that I start in state 2 and go to state 1. I can see that's 2 over 3. And finally, P sub 2, that's the probability you start in state 2 but end up in state 2. I can see from the diagram that's 1 over 3. Remember, as a sanity check, these probabilities have to add for each row to equal 1. So notice if you add, these equal 1 for the first row, and when you add these numbers straight across on the bottom row, they add to 1. If not, you made a mistake. If each row doesn't add up to 1, you made a mistake somewhere. Okay, so some questions are just asking you to take a diagram and convert it into a matrix. All right, so let's go down a little bit. Let me just show you one item that there are some diagrams that might be a little trickier. So here is a diagram with 3 states, but it's going to be the exact same setup. You're going to want to know the probability. So let's write this out. I'll write the first row maybe. And you can see this is going to be a 3 by 3 matrix on this one. So the way I'll write this is P sub 1, P sub 12, and P sub 13. Okay. All right, now I've got to know what is the probability that I'm in state 1 and I stay in state 1. Now notice that's not marked on this diagram. But what I'm noticing is this probability is 0.7 coming out of state 1. That's going from state 1 to state 2. This is the probability of going state 1 to state 3. So that must mean this probability is 0. right? Remember, the probabilities coming out of any state must always add up to 1. So that means I'm going to put a 0 here. All right, let me do P sub 1, 2. That's the probability of going from state 1 to state 2. You could see that's 0.7. And what about P sub 1, 3? That's the probability of going from state 1 to state 3, and I can see that's 0.3. All right, so that should let you fill in the row here. And it can even get more complicated. Let me go down. Here's a diagram with 6 states. Now notice there's a lot of zeros here because notice, let's say you want to go from state 3 to state 6. Well, there is no arrow from state 3 to state 6. So if there's no arrow, you can assume that transition is a 0. So when you look at this matrix, notice there's a lot of 0 entries because there's a lot of transitions that are not documented. And if there's no indication, then you can assume that's 0. All right, let me go back and do a couple of other problems. How about if we go back, let's do number 3. All right, so folks, a good first step for any of these kinds of problems is to write out the diagram, because if you can write out the diagram, then you can translate that into the transition matrix. All right, now what they're telling me here is think of state 1 as being this sorry boogie board, and state 2 is the C&T board. So let me draw that diagram. State 1 is sorry, and state 2 is this C&T board. All right, now I'm going to mark down the transitions. It says half of sorry switch to C&T. So half of sorry switch to C&T, while the other half remain loyal to sorry. That means the other half are staying with sorry. Okay, 3/4 of C&T stay loyal. So that means 3/4 stay loyal, 0.75. And the rest switch to sorry. Well, if 0.75 are loyal, that must mean the other 0.25 are switching to sorry. All right, so now I have the transition matrix, right? I'm going to enter 0.5 here. That's the probability of going from state 1 to state 2. This is the probability of, I'm sorry, this is the probability of going from state 1 to state 1, which is 0.5. This is the probability of going from state 1 to state 2, which happens to also be 0.5. And then this is the probability of going from state 2 to state 1. That was 0.25. And then finally here is P sub 2, that's the probability of staying in state 2. When you start in state 2, that's 0.75. All right, so that's filling in the matrix. Now what this is asking me is what's the probability that a sorry state board is going to be using the same brand 2 seasons later? Now notice in this problem, they're not giving me any kind of an initial distribution matrix. They're not saying to me, here's the percentages right now for market share. What happens 2 seasons later? Instead, they're asking me to calculate the probability that a sorry state board will stay using the same brand. Really, they're asking me to calculate this P11 2 seasons later. Well, to do that, I'm going to take the transition matrix times itself. So I'm going to take 0.5. Here's the transition matrix. And I want to know what happens after 2 seasons. So I'm going to take this transition matrix and multiply it by itself. I'm sorry, this should be 0.75 down here. Let me fix this. This is a typo. This should be a 0.75 down here. All right, so I'm going to multiply these matrices together. Now, I really don't have to bother doing the whole matrix multiplication because all I really need is this new P11 number. So really all I care about is this new P11. So all I'm going to do to get that number, you remember matrix multiplication, all I need to do is take this row times this column. So let me work that out. That's going to be 0.5 times 0.5 plus, so I'm going to write this as new P11 plus 0.5 times 0.25. And if you work this out on your calculator, you'll get 0.375. So this new probability that a sorry board owner will stay with a sorry board owner after 2 seasons has dropped to 0.375. Okay, so in this one, we just took the transition matrix times itself. I didn't have to do the whole matrix multiplication. You could do it if you want, but all I needed was this cell in the upper left-hand corner. All right, let's do another example. But if we do number 4, this is a little different. So again, the first thing I'm going to do on this problem is make up a transition diagram. All right, and here's their instructions. It says, let's state 1 be a business major, and let's state 2 be a non-business major. Okay, so let me do that here. All right, and now let's take the wording of this problem and come up with the diagram. All right, so let's read what this problem is saying to us then. It says 40% of business majors switch. All right, well, that means that I should draw 0.4 as this probability going from state 1 to state 2. Of course, that tells me that the other 60% must be staying as business majors. Okay, then it says non-business majors, 20% switch back to business. I'm going to put a 0.2 here, and that must mean that the other 0.8 stayed. All right, so let's write this out. This is P11. That's the probability that the person stayed as business. That's 0.6. P12 is the probability that someone switched. That's 0.4. And P21 is the probability that someone went from non-business to business. That's 0.2. And finally, 0.22 is the probability that someone was non-business and stayed. All right, so now they're asking us to calculate the probability that a business major will no longer be a business major in 2 semesters. All right, so again, what they're asking me to do is take this transition matrix and multiply it by itself to see what is the impact after 2 semesters. All right, so I'm going to multiply these together. Now, again, I don't have to do the entire multiplication. I just need to figure out what cell do they want in this answer. Right, so here are the 4 cells that I could calculate, but I only need one answer here. Well, what they're saying is a business major will no longer be a business major. Well, for that, what they're really asking me to figure out is P sub 1, 2, right? This is P sub 1, 2. The person starts out as a business major, but changes to be a non-business major. So P12 is this cell right here. All I need to do is figure out this box. All right, well, if you remember matrix multiplication, to get that answer, I just have to take this row and let it multiply that column. So let's do it. 0.6 times 0.4 plus 0.4 times 0.8. And if you work this out in your calculator, it's 0.56. So the probability that a business major will change to be a non-business major after 2 semesters is about a 56% probability. All right, let's do a couple more examples. We go to number 5. All right, so number 5 is asking me to, so in this one, they actually are giving me
the initial distribution vector. They call that V. Right? If you read the textbook, V is the initial distribution vector. All right, part A. Find the two-step transition matrix. And they call the transition matrix P. Well, for part A, they're really asking you to take matrix P times matrix P. Those are the examples we've just been doing where we found the two-step transition matrix by taking the matrix, the transition matrix times itself. So you're going to take the transition matrix times itself. I'm sure you remember how to multiply matrices together. So if you multiply this matrix times that matrix, you'll get this answer shown here. All right, let's go to part B. Part B says find the distribution vector after one step. Well, really what this is asking you for part B is take V and multiply it times the transition matrix. Okay, so I'm going to take the initial distribution vector, which is 1, 0, and multiply it times P. This is not going to be as bad as it looks because there's some zeros floating around here, and we have zeros. The multiplication is a little easier. So when we work this out, I'm going to take 1, 0 and multiply it times this column. So for this answer here, I'm going to be taking 1 times 0.2 plus 0 times 0. So of course that's going to be 0.2. And then for this entry, I'm going to be taking this row times that column. So that's going to be 1 times 0.8 plus 0 times 1. So that is 0.8. So 0.8 answer. Okay. And again, remember, the sum has to be 1. So if the sum of these is not 1, you know you made mistakes. All right, let's go to this question. It says, what's the distribution vector after 2 steps? Well, what I'm going to do for this problem is I'm going to take my answer from part A and multiply it times the transition matrix one more time. Because this answer, 0.2, 0.8, is the result after 1 step. Well, if I take that result after 1 step and multiply it by the transition matrix, I'm going to get an answer that's the result after 2 steps. Right? Every time you apply the transition matrix, you're getting another result for another step. Okay? And so we could just multiply these out. I guess we can do it real quick. I'm going to take 0.2 times 0.8 and let it multiply this column. And if you do that, you'll get 0.04. Then I'm going to take this row times that column. And if you multiply that out, you'll get 0.96. Again, notice how these probabilities add up to 1. And then the last part is going another step. So I'm going to take my answer after 2 steps, which is 0.04, 0.96, and again multiply it times the transition matrix. That will get me the result after 3 steps. Okay, I'll let you do that. Okay, and folks, there's a worked out example in the textbook. So please check out some of the worked out examples. That'll show you how to set this up. All right. So let's see if there's anything else. Some of these are very similar. Just looking if there's anything else. Let's do 15 and 16. 15 and 16 are very similar because 15 and 16 are both asking to find what's called a steady state distribution vector. Okay, and really that's what question 16 is asking. Question 16 says, in the long term, whenever you see that kind of terminology, it means find the steady state vector. What does that mean? Well, it means you start out with V, the initial distribution vector, and you find out what happens after one step. Then you want to know what happens after 2 steps, after 3 steps, etc. What about after many, many steps? Well, it turns out that distribution vector that you started with settles to a final answer. And if you keep applying the transition matrix over and over, you get the same answer. So it's kind of like in steady state, what happens is you start out with some kind of a distribution vector. And when you apply the transition matrix, you end up back to the same vector that you started with. It's kind of like now you're applying the transition vector and you're not getting any different result out of it. That's how you know it's the steady state vector. And this is worked out on an example 4 on page 560 in our textbook. So this is the idea. We want to find out what happens when you apply the transition matrix many, many times. And there's a shortcut way to do it, because I don't want to sit here and multiply, by the transition matrix 100 times to see what happens. So let's do number 16. I think 16 will give us a good view as to what this procedure is. Let's go down to number 16. All right, well, what I'm going to do first is set up the transition matrix. All right, so let's read this. It says there's a high risk category, okay, and a low risk category. All right, it says a high risk motorist has a 50% chance of staying high risk. So I'm going to draw that as 0.5. And a 50% chance of moving to low risk. All right, I'm going to draw that as 0.51. Low risk has a 10% chance of going to high risk. So I'm going to write that as 0.1. And a 90% chance of staying low risk. So I'm going to write that as 0.5. All right, so now I can write the transition matrix. Remember, this is P11. So that's 0.5. P12 is 0.5. P21 in our example is 0.1. And P22 in our example is 0.1. All right, so this is the transition matrix. Here's the way we can solve this. What we're trying to find is an initial vector, let's call it xy, such that if I multiply it by that transition matrix, I end up with the same row vector. So what happens is, after in the long term, by applying the transition matrix, the initial vector doesn't change. We call that steady state. It's kind of like you've settled down to a distribution, a percentage of motorists that is not going to change over time. All right, so I need to solve this equation. All right, well, let's multiply this out and see what happens. I'm going to take this row vector and multiply it times this column vector. That gives me this answer. All right, so I'm going to do it. That's going to be 0.5x plus 0.1y. That has to equal this answer over here, x. All right, we do the same thing with this row vector times this column vector. And that's going to have to equal the result y. So that's going to be 0.5x plus 0.9y equals y. I need to solve this system of equations for x and y. All right, the first thing I'm going to do is in this first equation, let me subtract x from both sides to get the x's on one side. So I'm subtracting x's there. If I do that, that's negative 0.5x plus 0.1y equals 0. And for the green equation, I'm going to subtract y from both sides. If I do that, I'm going to get 0.5x minus 0.1y equals 0. All right, now it turns out I really can't solve this system the way it is now. Because if I was to try to solve this system, or if I was trying to add these two equations down, straight down, you might remember the elimination method from algebra, I would get no solution out of that. So these two equations are redundant. They're really the same equation. So I need a new equation. But the new equation goes back to the fact that these two probabilities must add up to 1, if you remember. So I can throw a new equation into the mix that x plus y equals 1. All right, now let me try to solve this system of equations using, let's say I'm going to call this equation A and equation B. All right, so let's try to solve that system. Maybe I'm going to come up here to the top and give a little more room. And we're just going to solve this system of equations. This goes back to algebra. You probably remember this. So let's write out equation A. This is negative 0.5x plus 0.1y equals 0. And now I'm going to write equation B as x plus y equals 1. All right, I want to solve this system. I could use substitution method. I could use elimination method. Here's what I'm going to do. I'm going to take equation B and multiply by 0.5. Because I'm seeing that I can probably eliminate x here. So let me do that. That's going to be 0. I'm multiplying both sides of equation B by 0.5. So I'm going to multiply this side by 0.5, and I'm going to multiply this side by 0.5. So that's going to give me 0.5x plus 0.5y equals 0.5. All right, I'm going to take the blue equation and just copy it over. So that's negative 0.5x plus 0.1y equals 0. Now I add these equations straight down. If I add these equations straight down, negative 0.5x and positive 0.5x cancel out. When I add the y terms, that's a 0.6y. And when I add these constants, that's 0.5. So it looks like y equals 0.5 over 0.6. So it looks like y equals, I guess I'll work this out on my calculator because they want me to round this to 2 decimal places. So if I work this out on my calculator, and I'm working out 0.5 divided by 0.6 on my calculator, I'm getting 0.8333. But they want the answer in percent form, so this has to be 83.33%. All right, well, I know that x plus y equals 1. So if I know that y equals 0.833, then x is 1 minus y. So that's a 1 minus 0.833, which is 0.1666, which is 16.67% when I round to 2 decimal places. So to find the steady state or long-term distribution vector, what you have to do is take a row vector xy multiplied by the transition matrix, and you got to get back to that same vector xy. But to solve this system of equations, you got to throw one more equation into the mix. You got to use the fact that when you add x and y, those two probabilities have to add up to 1. And of course, you can see that these two probabilities do add up to 1 when you add them together. All right, folks, hope this is helpful as you're working in the Module 11 homework. Let me know if there's any questions.